I am Dr. Ashanendu Mandal. I am now speaking from Kolkata, India. I am basically a person from industry. I worked with premier oil and natural gas company, which is called ONGC, for more than 34 years. This particular presentation is based on my own research work, which is carried out in University of Calcutta. This is for basically wastewater treatment and to take care of the environment. So the title of my presentation is Potential Application of Innovative Solid Waste Materials for Adsorptive Removal of Toxic Phenol from Wastewater and Generating Circular Economy. So from the title, you can see there are very important features involved with this particular research work. First of all, it is for the wastewater treatment. So definitely the environmental pollution which is supposed to be there because of toxic phenol, that can be now will now have any problem after this particular adoption of this procedure. Secondly, you see this water can be reused also, recycled also. So when there will be a scarcity of water in the industry or in a particular refinery, for example, or in any petrochemical plant which is getting polluted because of phenol, but there is a fresh water scarcity also, this water can be reused or recycled. Third, you see, it is basically on the principle of adsorption, which is very simple, does not involve much cost, and anybody or any industry or any small scale industry also even can go for this particular procedure or method. Fourth important aspect is that it is using the solid waste materials. So, and these waste materials are available all over the world at almost zero cost. So this is a very important from the availability of the materials as adsorbent is concerned. And finally, when we will see the materials or study phenol is a very important material because it is used for manufacturing resins, which is required for the construction purposes. For that, it is produced through the hydrolysis of chlorobenzene or oxidation of isopropyl benzene. But phenol as a pollutant also is possible to be produced as a byproduct in the chemical industries. For example, refineries can discharge up to 500 ppm in their wastewater. Coal processing can go up to 6,800, coking 3,900, and petrochemicals 1,220. And besides industrial wastewater, you see phenol is also available in domestic and agricultural runoff because of the use of insecticides or pesticides. Why we are talking phenol as a pollutant? Because of its toxicity. And that toxicity can cause cancers or chronic diseases. Not only on human body, it also affects the soil as well as groundwater. So there is a allowable limit of phenol in discharge water as per EPA US and Ministry of Environmental Concern in India up to 1 ppm. And for potable water, it is 0.001 ppm. There are many methods available, in fact, other than adsorption also. They are not that much popular, or we can say nowadays getting replaced by adsorption. But those procedures are named as polymerization, electrocoagulation, extraction, filtration, photodecomposition, electrophenol methods, advanced oxidation process, enzymatic degradation, microbial degradation, membrane-based separation, and ion exchange. So adsorption, what it is actually? It is basically a process that occurs when a gas or liquid solute accumulates on the surface of solid adsorbent. So for this particular research, phenol is getting adsorbed on the solid adsorbent surface. It can happen either physically or chemically or both. In case of physical adsorption, the van der Waals forces is responsible for its bonding. And in case of chemical adsorption, it is because of chemical bonds such as ionic and covalent bond. So physical adsorptions are reversible. So that's why the disruption also is easily possible. So if we would like to regenerate the adsorbent after adsorption also can be possible because of this reversible nature. But in case of chemical adsorption, it is irreversible. So once the chemical bonding is taken place, it cannot be reversed back. So the disruptions will be difficult for getting back the regenerated adsorbent. And finally, you see physical adsorption is basically a multimolecular layer, but chemical adsorption is unimolecular. In our objective of the study, we have taken basically 8 adsorbents, solid waste materials. 4 are from biological waste and 4 are from industrial waste. The biological waste materials are from guava tree bark, rice husk, neem leaves, and activated carbon from coconut coir. And industrial waste adsorbents are rice husk ash, red mud, clarified sludge from basic oxygen furnace, and activated alumina. So you can see all the adsorbents, either it is biological waste or industrial waste, are plentifully available almost all over the world. And now we will go for their characterization also to understand what sort of mechanism is taking place and what sort of potential of adsorption is likely to happen in those materials. So for that, we will have ACM, XRD, FTIR, BET, and point of charge. In our objective of the study, we have first carrying out the batch process, and for that the process variations will be initial pH, contact time, adsorbent dose, temperature, and initial phenol concentration. These physical parameters are very important and can be regulated easily also. And we have varied it to find out the optimum or maximum adsorption percentage to be obtained. And this data is then analyzed for the modeling purpose also. We have done the kinetic study, which is basically related to the time, the isotherm study based on the equilibrium conditions at a particular temperature, and thermodynamic study, which is related to the change of temperature or variation of temperature. Then we have got the prediction analysis through artificial neuron network. This is the first time we have utilized in adsorption scenario. And if we would like to take our research activity to our commercial applications, then we need to have some more study like scale-up designs, means how much quantity of adsorbent will be required for certain volume of wastewater under certain percentage of phenol. That can be calculated. Regeneration of adsorbents, although the adsorbents will be available freshly at almost zero cost, but even then, if there is any short supply, we would like to regenerate it. So that is also possible. And for that, we have studied how it looks like. Then we have taken the real industrial wastewater also. Although we have prepared the phenol solution or wastewater in the lab for our study, but we have taken the industrial wastewater also for verification. And finally, we have got the safe disposal procedure also, how safely it can be disposed of after this phenol adsorption. And then we have gone for the column study also, because in many industry, we may have to go not the batch process, but the continuous process. For that, we have taken neem leaves as the adsorbents. Only one adsorbent we have taken here, and that adsorbent is the best adsorbent from the potential point of view and the percentage renewable point of view, which we have got through the batch study. And for our column study, we have taken the variations like bed height. Bed height is basically based on the change of quantum of the dose. Flow rate is based on the time and initial phenol concentration. The other two parameters like pH and that is what we have maintained in the batch process is kept constant in this case. Now here also we have done the modeling like kinetic study, isotherm study, and finally we have a comparison of adsorption capacity, what we have got in neem leaves vis-a-vis what other researchers have got in their study while they have done. And we have understood and studied the mechanism of adsorption also taking place both physically as well as chemically. And for column study also we have taken real industrial wastewater, scale-up design, regeneration of adsorbents. And for prediction other than ANN, we have done the MLR analysis also. Now let us go for the adsorbent preparations. First we have prepared the guava tree bark. It is taken from the guava plant. You can see from the picture. And that bark is taken, it is washed, dried and powdered, and we have taken the -44 plus 52 mesh size. This procedure basically the washing and drying and grinding is considered for all the adsorbents. Like this is rice husk. For that the materials is collected from the rice mill, neem leaves, which is collected from the neem trees, which are available everywhere. So we have collected, washed, dried, and taken the powder. And this is the coconut coir. Now, coconut coir, instead of using directly as adsorbent, we have basically first converted it to activated carbon so that its potential is increased, potential of adsorption is increased. For that, this coconut coir, after washing and drying, that powder is taken into a furnace and kept at 800 degrees centigrade for 1 hour to ensure that the activated carbon is coming from the coconut coir powder. Then the industrial waste, we have taken the rice husk ash. The rice husk is basically utilized in many cottage locations or rural areas as fuel, and that can be basically for that the rice husk which is collected from the mill will be used as fuel, and then that can be taken in our adsorption preparation purpose. Then we have taken the red mud which is collected from the aluminum plant. We have taken the clarified sludge. This is from the steel furnace. In the steel furnace, steel manufacturing unit, we have low carbon steel conversion from molten pig. There we will get this sludge, and that can be used. And finally, the activated alumina, which is also available in the aluminum plant, that can be used as an adsorbent. Now we will prepare the wastewater. For that, the phenol is dissolved in distilled water, and we take 1 gram of phenol in 1000 ml of distilled water. So we get 1000 ppm, and that can be diluted as per our requirement for changing the initial phenol concentrations. And after adsorptions, whatever is the remaining phenol percentage, that can be measured through UV absorbance instrument. We will basically measuring the absorbance which is related to the phenol percentage. So with the known percentage of phenol, first we prepare the calibration curve, and then for unknown scenario from the calibration chart we can calculate after measuring the adsorbance what is the residual phenol percentage. pH is measured in pH meter, and pH is changed with the addition of sodium hydroxide and HCl. Now this is the batch experiment schematic diagram. Here you can see basically in a beaker of 250 ml, we have taken 100 ml of phenol solution. The concentration varies from 5 to 500 ppm or milligram per liter, and pH is varies from 2 to 12, and the dose quantity is measured in the measuring balance, and that is what we have seen is required from 0.1 to 0.25 gram per liter. And then that beaker is placed in a mechanical shaker where the contact time is maintained from 30 to 600 minutes, and we ensure that within this particular time the equilibrium has taken place, and the temperature variation is 25 to 50 degrees centigrade. That temperature variation is important because the ambient temperature is not constant everywhere, so that will let us know what sort of percentage of phenol is coming based on the temperature variation, and it can be otherwise utilized for thermodynamic study for modeling also. Then after this mechanical shaker, after all these conditions are maintained with the variations, we filter it, and that filtered is taken for absorbance measurement, and from that absorbance we come to know the residual phenol. So we have got the initial phenol percentage, and now we are coming to know the residual phenol. Then we can calculate whatever. I'll show you what the calculation is required. So these are the for 8 adsorbents, these parameters variations, and this is the calculations which is required for removal of phenol percentage. The initial phenol concentration minus the final phenol concentration divided by initial phenol concentration into 100. And for phenol adsorption capacity is based on the adsorbent. So the C0 minus Ct divided by Ms. Ms is the weight of the or mass of the adsorbent. So we get milligram phenol removed in gram of adsorbent. So milligram per gram is the unit for adsorption capacity. Now in the results and discussions, first we have done the ACM as I have said. And in ACM, we have taken the topography, and every picture, all these 8 pictures are for 8 different adsorbents, and they are showing a lot of pores are there. So the pores are very good for adsorption because pores increases the surface area. So this is a good indication that there is likely of physical adsorptions definitely would like to happen because of this topography. Then we have done the XRD study also. In the XRD study, we have whatever results we have got, that is basically graphed 2 theta versus intensity. And for all the 8 adsorbents, what we find, there are peaks. And these peaks are basically the crystalline nature. And more the crystalline nature, more will be the surface area. So that is good for adsorption. Then we have got the FTIR study also. The x-axis is the wave number and y-axis is the intensity. Here you can see the downward peaks are there. These peaks are basically because of the functional group. And so FTIR study conveys that based on the wave number, these are the functional groups available in the adsorbents. And these functional groups are responsible basically for the chemical adsorptions. This can be helping either, you can say hydrogen bond or pi-pi bond. So finally, other than the characterizations through those units, we have taken the physical properties measurement also, like bulk density, surface area, effective particle diameter, and point of zero charge. The surface area is measured based on BET. This is a good indication for knowing the adsorption capacity. And point of zero charge is basically, this is a particular, this is done through the sodium nitrate salt addition drifting method. So at this particular pH, the surface of adsorbent is neutral. Now, in our batch study, we have done the process variations vis-a-vis the percentage removal of phenol. So here you can see for 8 pictures are there. They are for 8 adsorbents, and there are 5 lines are there. This is for 5 different concentrations, and the other things are kept constants like contact time, adsorbent dose, and temperature are constant. So if the pH is varies, we see there is a peak for all the pictures. So that means at that particular pH, the percentage removal of phenol is maximum. So this is the optimum pH. We should try to maintain that pH for maximum removal in the commercial applications. But another thing also you can say, if the pH is varying a little here and there, then also the percentage remains high. So it's not essential that pH needs to be maintained at this critical pH, but if it is easily to be possible to maintain, then we can look for that. Then if we look for contact time variations, the other things are constant, and the 5 lines are for 5 different concentrations. And for every adsorbents, you can see here that initially the less contact time, the pH variations, the phenol removal will be less. But if we give more time, the ultimately phenol removal will be maximum. So that is the optimum level or equilibrium level. And after that, no more phenol will be separated out. So this is the reaction time, we can say. While we will design the reactor, this much retention time we will have to maintain for getting the maximum removal percentage. Then effect of adsorbent dose. If we change the dose quantity, here also you can see the removal percentage increases. That is obviously because of more and more adsorbent surface are getting added. So more removal will take place. But again, this is also going to be constant after a certain time, because in a certain volume of the reactor, if we go on adding more and more adsorbent, then the agglomeration will take place, and finally the surface area will go down. So there is a maximum limit of quantum of adsorbent dose which is required for that particular condition. Then with the temperature variation, what we find that in certain cases the removal of phenol is increasing, in certain cases it is decreasing. The increasing means it is the endothermic reaction, and decreasing means it is the exothermic reaction. So when the chemical adsorption is taking place, that time the heat is either being generated or we will have to put external heat. So based on that, this endothermic and exothermic natures, the behavior of the phenol removal percentage varies. And finally, if we increase the initial phenol concentration, you can see the percentage removal is going down. That is because at higher phenol concentration, the total adsorption sites are inadequate. Now, this is very important what we have got in our experiments in the batch process. For all the variations, there are plenty of variations taken place. And finally, what we have got under critical conditions and optimum conditions, the maximum removal percentage of guava tree bark is 90.67, rice husk 94.74, neem leaves 97.50, coconut coir 95.20, rice husk gas 93.33, red mud 87.50, clarified sludge 63, and activated alumina 21.8. So the maximum removal percentage is neem leaves, and that's why we have taken the continuous study or column study with neem leaves as adsorbent. And these are the kinetic studies. So time is less, we will not be explaining, only we will be letting you know what are the results we have got in the modeling. In kinetic first order and second order model, pseudo first order and pseudo second order for all the 8 adsorbents. What you have got only for red mud, it supports pseudo first order. Pseudo first order means it is basically physical and homogeneous. And for all other cases, the chemical adsorption persists more compared to the physical adsorption. Then we have done the Reichenberg model that shows that field diffusion have taken place. The Fick model has told basically whether the film diffusion or the interparticle diffusion, or basically the rate determining step is identified through this modeling. Then Ilovic model says all are chemical adsorption. Furusu and Smith model says that there is a renewal movement, that is phenol moves faster from bulk to solid stage very fast. And Boyd model says that they are all chemical adsorbents. Then we have gone for isotherm study. So after kinetic study, we have done the isotherm modeling, and for this the temperature is constant, but the equilibrium condition varies. Based on that, we have done the Langmuir model, Frenluch model, Temkin model, and DR model. Very important modeling in isotherms, all have been tried with our data. And finally, we have got Frenluch isotherm, which is very much supportive for guava tree bark, rice husk, neem leaves, coconut coir, red mud, and activated aluminum. Only Langmuir is supportive for rice husk gas, and DR is for basic oxygen furnace. And from Langmuir, actually, you can see in the first top portion of the data that Qmax is there. That is the maximum potential of adsorption. So that is showing that 980 is for coconut coir because it is activated carbon. So that's why the maximum potential of phenol removal has happened, and it is almost 980. For other cases, it is 44, 50, 74, 13, 39, and like that. But for coconut coir, it is maximum. And then we have got the thermodynamic study. It is with the variations of temperature. And here we basically, through this modeling and graph, we calculate the del G value, del H value, and del S value. That is, gives free energy, enthalpy, and entropy. And we can get negative or positive. If it is negative, del G, that means it is spontaneous. If del H is positive, it is endothermic. And if del S is positive, it is random. So what we have got, that all the 8 adsorbents having spontaneous adsorption. So this is very good for adsorption because all are spontaneous. We have got out of 8, 5 are endothermic, that we have seen on in our experiment batch study also. Here through the modeling also we get the same result. And random is for rice husk gas, red mud, and clarified sludge from basic oxygen furnace. Then we have done the ANN modeling. As I said, the prediction analysis is done through the utilization of artificial neural network. So for that, we have got total 813 data. Okay. So we have done the LM modeling and SCG model, and we have finally got the results that the percentage which is coming out from the experimental as well as through this modeling are more or less same. Now scale-up design, based on that we have calculated what is the quantity of adsorbent required, and minimum adsorbent quantity is for coconut coir. Regeneration we have done, there is a desorption procedure we have done through distilled water as well as through ethanol solution, 30% ethanol solution we have done. And then we have calculated their adsorption potential. Up to 2 cycles they can be utilized. And real industrial wastewater we have taken from coke oven plant, and we have studied that, and we have got more or less the same potential. So that means whatever we have examined in our laboratory, that is also okay, as well as industrial wastewater also is okay. Safe disposal we have done, and we have taken it to brick industry. In the brick manufacturing, if we are mixing with other ingredients, then also we find that it can be disposed of, and it can generate the circular economy. In the column study, we have taken the phenol solutions, and peristaltic pump is there. And the column, basically, we have taken the adsorbent. And finally, we have in the effluent, we have measured the phenol removal percentage. And these variations are bedite, flow rate, and phenol concentrations. We have got the breakthrough curves also. And the bottom is, you can see x-axis is time and y-axis is Ct by C0. The flat portion, that means there is no removal of phenol after adsorption. So this is good, and that is the time which is required for column continuous process. These are the calculations, and the kinetic modeling we have done. Boat Adams, Thomas, Yun Nelson, Ulborska Ashanendu model and modified dose response, and Ashanendu model is the best. And isotherm we have done Langmuir and Frenluch is the best. And if we compare the adsorption capacity of neem leaves in a continuous process vis-a-vis other adsorbents which are studied by other researchers, we find that the neem leaves also has got very good potential for phenol removal. And in the mechanism, you see, it has got both physical as well as chemical adsorptions. Physical is basically the film diffusion, the bulk diffusion, and interparticle diffusion. Whereas for chemical, it is because of H bonds and pi pi. That is mainly because of the cellulose availability in the neem leaves. And real industrial wastewater we have checked and got almost the same figure. Scale up design, we have calculated what is the bed height required, and regeneration also we have studied. And now for predictive analysis, we have done the MLR study also, that is the column multiple linear regression study. And we have evaluated an empirical formula based on the process variations. And this way we can predict in the unknown scenario what is the maximum removal of phenol. And we have done the ANN for column study also. We have got more or less the similar results what we have got in the batch study, and we can see that this ANN holds good for column study also. So finally, what we can conclude that the 8 adsorbents, 4 are from biological and 4 are from industrial. They are plentifully available all over the world at almost zero cost. They can be suitably utilized for removal of phenol, and for that we have checked in various ways, not only experimental but also through the modeling. And after that we have also studied for their commercial suitability, what is the quantity of requirement of adsorbent will be there, what is basically the conditions to be maintained, and regeneration, how effective it will be. All those things have been studied, and finally we can conclude that as it is, the spent adsorbents can be utilized for big manufacturing also, so it can be used for circular economy. So as the adsorption is very simple and the cost involvement is very less, I basically I can convey that the many small scale industries who cannot afford much expenses for other procedures, they can right away go for this batch or continuous study, a continuous process for phenol removal with the use of any of the adsorbents, but neem leaves will be best for them. So these are the papers which are published. Thank you. My email address is given for any contact which is required later on, ashanendumandal@gmail.com. If any question comes right now, it's okay for me. Otherwise, you can email me. Thank you. Thanks. Thanks a lot.